What up, Eastview Scholars? Now, at this point, we have started doing some math with conversions and density problems, so it is time on this edition of Sharp Shorts to talk about significant figures. Now, significant figures can be many things. For you, it could be the President of the United States. If you're into medicine, it could be Hippocrates. Or, looking at this picture here, it could be this handsome warrior right here flashing the badger sign. In chemistry, though, and in many sciences where we are working in lab, collecting data, measuring data, calculating with data, significant figures really are a determination of, are your numbers accurate or are they precise? And while many people think those are the same things, they are not. Accuracy and precision are actually two different things. You can be very precise without being accurate, and I'll use this dartboard as an example. Say I was aiming with my 3 darts for the bullseye, but my darts hit here, here, and here. They all cluster together nicely in the 18s there, but in relation to what I wanted to hit, which was the bullseye, it wasn't very accurate. Very precise, not very accurate. On the other hand, if my darts or the person I was playing, their darts hit here and here and here, not only did they have a nice precise throw with all their dots clustered together, but they were hitting a bullseye. So that is a difference. And that is something that can happen in the lab. Accuracy determines and discusses how close you were to the accepted value or the target value, something along that line where you know where you want the outcome to be. Precision just talks about multiple, anything more than 1, 2, 3, 4 sets of data trials that you're doing. They can all be very precise, but maybe not very accurate, but it requires multiple points of data. Okay. How does that apply to us? Well, we have to think of the measurement here. I've got a little piece of metric measuring tape here, and we want to reflect the accuracy because in reality with all the measurements you're only as accurate as the tool you're using. Now say I was using this, and we don't have the whole thing from 0 in here, but I was using this to measure a piece of wood, so I would start at one end, the left hand side say, and put the tape measure down, then run it along until the end. And say that end happens somewhere in here. Okay. At that point, I can pretty accurately determine that we were at 1,000, reading my gradations here, 1,037. Those are actual numbers I can read right off the ruler. Point, I'm going to put my decimal in there, and then my last number always in determining a measurement is a guess. But it's a very precise or very close to accurate guess because in between these two little millimeter lines I could certainly get very close, and let's just say that that's 0.3. Okay. That's about all I can do because that's the best I can do is use all the lines and then the last gap in between the lines, which I can estimate, and the last number is always estimated very well. I could not just determine that this is 1,037.3, let's make up some numbers, 2, 5, 9, 6. And you know as well as I do, I can't do that because this was just guessing. Well, that's true in measurements too, and where that's going to come into play in our class here is calculators. Okay. Calculators are wonderful tools, but that's what they are. They are a tool. They are not a measuring device. Here is my ancient Hewlett-Packard. I can set this screen to show me anywhere from 1 to 9 digits. It will round the answer depending on how many digits I want to display. Okay. Just because I have more numbers does not make it more accurate. I could not measure the 2596 down here, and I don't have tools in the school or tools around that could measure a length this way. Just like if I was doing a mass, I can maybe get to 1/10 of a gram, or we have some scales that will maybe go to the milligram, the thousandth of a gram, and that's as accurate as we can get. I can't just add in numbers. And when I'm using that data and calculating with it, I also cannot just use all the numbers that show up on my calculator. That is not more accurate. In fact, that builds an error and gets you away from the accuracy you want and becomes less accurate. Okay? So our key here in this video here is just to give you a brief outline to say, when I look at numbers, how can I tell which ones were the significant digits, the ones that were important in the measurement, and which ones were placeholders or numbers that need to be rounded off. And it comes to this question I was asked again the other day as we were doing math. Where on the number do you want us to round off in this class? Basically asking what you've been told in other classes or math classes and stuff. They give you a set number and say, just round here. Well, in reality, rounding should be based on the tools you use for the measurement. Okay. So when I'm looking at a number, what numbers are significant? Well, I've narrowed it down to 2 rules. You can go read your Pearson textbook and it will have more rules there, but it really comes down to 2 rules. When I'm looking at a written number, any number 1 through 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, all non-zero digits are significant numbers, meaning they were actually measured by the tool. The question then becomes zeros. And zeros can either be measured. I could certainly measure 101 pounds or 10,001 centimeters or something along that line. Or they might be placeholders to tell me that this number was rounded off in this area. And placeholders are valuable. They are not valuable in measurement, but they are valuable in understanding the magnitude of the number. So really, if you can count any of the non-zero digits and determine which of the zeros are placeholders, you can determine how many significant digits are in a given number. And then, as we'll see in the next example, once I use that when I'm doing my calculations with it, then I can round my answers that will give me the best percent error, best accuracy I can get. Okay, so let's look at these numbers. And here's our placeholder zeros. Placeholders occur in one of 2 spots. At the start of a number, at the end of the number, on the left or the right. Okay, this is very simple. Numbers preceding, this is a number less than 1. Zeros preceding any non-zero number are not significant, they're placeholders. Just think about it. I have a number here, 0.0045. I can't measure anything till I hit the 4. 0.00 wasn't a measurement. I can't measure a length at 0.00. I couldn't measure if I was measuring my height. 0.00 doesn't tell me anything. If I was measuring a mass, a chunk of gold, 0.00 isn't a measurement yet. I have to move away from 0 to get a measurement. So for any number, the significant digits don't count until you're going from left to right until the first non-zero number. So these are placeholders. They are valuable in telling me that this number is less than 1. Okay? But the only significant digits, this number has 2 significant digits, the 4 and the 5. Now, same here. Okay? There's a whole mess of zeros right here. But they are placeholders to tell me the magnitude of this number below 1. I only have the 5, the 6, the 8, as non-zero rule number 1 numbers. Those are significant. Then I have a 0. Now it's not on the left, it's not on the right, it's in the middle. I call that the zero sandwich. Any zeros in between 2 non-zero numbers are significant measured digits. I certainly could measure a length that was 5,608, or in this case, below 1, whatever value that is below 1. So it could be 1 0, it could be 3 zeros, it could be 100 zeros. In between 2 non-zero numbers, doesn't matter, they count. Decimal could be in there too, they count. So this number actually has 4 significant digits. Okay? Again here, those 2 zeros cannot count, they're placeholders. I haven't measured anything till I hit the 9. So the 9 and the 8 count. The 0 in the middle counts. So then your question is, what about the ones at the end? Well, let's first go look at this rule and then come back. Zeros ending a number on the right hand side without a decimal are placeholders. You need the decimal to tell you accuracy. Okay? So here we have 100. The 1 is a significant digit because it's non-zero, but these two zeros without the decimal just tell you this number was rounded to 100. Okay? That's as accurate as you can get it as one significant digit. 25,000. The 2 and the 5 are significant digits, but the zeros here without a decimal in there only tell you it was rounded to 25,000. These are holding the place to let you know that the value was around 25,000, but you don't know it exactly. Okay? Here we have 2,067,000. This 2, the 6, and the 7 fit rule number 1. The 0 hits the zero sandwich rule, so I have 4 significant figures here. These last 3 zeros, because there is not a decimal anywhere in the problem, are placeholders to tell you the value was 2 million, but you don't count them as measured quantities. So when we go back up to this problem, these 2 zeros are at the end, but there happens to be a decimal in the problem, meaning those were accurately measured, so this number actually has 1, 2, 3, 4, 5 significant digits. Why is that important? Let's look at the math. It tells me where I round my answers, and here are the functions. If I am multiplying or dividing, my answer can have no more significant figures than the measurement with the least amount, because that tells me what my least accurate tool was, and your chain is always weakest at the weakest link. Your measurements must reflect the weakest one you did. Calculate the density of an object with a mass of 4.075 grams and a volume of 8 milliliters. Well, density is mass over volume. Okay, so it's 4.075 grams divided by 8 milliliters. Sorry about that, 8. There we go. Okay. That number on my calculator actually came out to be 0.509375. Okay. Now, that's great, but I really don't have a tool that measures that far down to that 5. Now I look here. That has 1, 2, 3 non-zero numbers, a sandwich. That's got 4 significant figures. 8.00, the 8. I have 2 zeros at the end. There's a decimal in the problem, so they all are significant. That has 3. 3 is my least significant figure, so counting from the left, the significant digits, not the placeholder, I go 1, 2, 3 numbers, and then I decide what to do with the 9 from the 3. Mathematics tells me that the 3 means stay the same, round down, so the actual answer here would be 0.509 grams per milliliter is the density of that object. Okay. That's the most numbers I can report in the answer because that's as accurate as my measurement tools allowed me to be. This stuff, even though it popped up on my calculator, is fluff. Okay. Now, adding and subtracting is very similar, but what you're looking at is the least number of decimals. So when we add these two together, we're actually going to round our answer. Since this only has 2 digits after the decimal, that's where we're going to round our answer. If I add these together, my number comes out to be 100.3598. Okay, but I have to round that down, or up. I have to round that to reflect that my weakest measurement was the 0.65. So after the decimal, there's the first one, there's the second one. I have to round the 5 with what the 9 tells me to do, which is round up. So that answer has to be reported as 100.35 to retain my accuracy. Oh, 36, sorry, rounds up, to retain my accuracy in measurement. At this point, that's it. Eastview Scholars, warrior on, rock on. And our next installment will discuss scientific notation.